In this video, we're going to look at some calculations involving polyprotic acids. So to help us illustrate these calculations, let's look at a problem. And this problem involves a weak polyprotic acid. And here's the problem. It says calculate the pH and the concentration of all species present in a 0.030 molar carbonic acid solution. And you're given the Ka value for each deprotonation step. Carbonic acid is a diprotic acid. If you would, pause the video and write a chemical equation for each deprotonation step and a Ka expression for each of those deprotonation steps. Pause the video. Okay. So here's our deprotonation step number 1. We have the fully protonated carbonic acid in water, gives us hydronium and the conjugate base, bicarbonate. And we can write a Ka expression. This will be Ka1. Where we have our products over our reactant. And here is the Ka value that was given in the problem for the first deprotonation step. Now the bicarbonate ion has another ionizable proton, so it can undergo a second deprotonation step in water. So here we have bicarbonate in water, gives us more hydronium and the carbonate ion. Okay. So both of these deprotonation steps are occurring in the same solution. Let's stress that. And we can write a second Ka expression, Ka2, similar to the first. We have products over reactants, and we're given the Ka2 value in our question. Now, let me mention a couple of things before we get right into solving this problem. So here's our problem, and we have our first deprotonation step. The strategy we want to follow is basically, let's break it into two parts. Let's take the first deprotonation step and let's calculate the equilibrium concentrations of all species, carbonic acid, hydronium, and bicarbonate. And we'll do that, of course, as we know, by setting up an ice table, substituting the equilibrium values into Ka expression and solving for X, just as we've done many, many times. Then we'll focus on our second deprotonation step, and we'll essentially do the same strategy. We'll calculate all the equilibrium concentrations from our second deprotonation step by setting up an ice table, substituting our equilibrium concentrations into a Ka2 expression, and solving for X again. Now, before we get into solving this, let me just mention a couple of things that you want to be careful of. Here's our two deprotonation steps, and we of course have some species that appear only in one dissociation step, like carbonic acid and carbonate ion. These only appear in either the first or the second. We do have some species that appear in both deprotonation steps, so I want to mention something about these just briefly. For example, hydronium. Hydronium appears in both deprotonation steps. You cannot have two separate concentrations of hydronium. Okay? You're producing some hydronium in the first step, and you're producing more in the second step. So we don't have two separate concentrations. That's a common mistake. Instead, we have one concentration of hydronium, which is the sum of the hydronium produced in the first step, which we calculate first, and then we do a second calculation where we calculate more hydronium. And the total hydronium is, of course, the sum of these. Now, another species that appears in both dissociation steps is the bicarbonate ion. Again, we cannot have two separate bicarbonate ions concentrations. We can only have one because all of this occurs in one solution. So the final or total bicarbonate is what is produced in the first step minus any bicarbonate that is lost or dissociated in the second step. Okay. So be aware of that as you're doing these calculations and understand what's going on in this solution as a whole. So if you would, pause the video and see if you can calculate the equilibrium concentrations of all these species along with the pH. Give it a try before you watch the solution that I'm about to go through. So pause the video and try it. So first thing we want to do is calculate the concentrations of all the species in our first dissociation step. Now I may go through this kind of rapidly, and if I do too rapidly, please pause the video and rewind it. But these calculations should be somewhat familiar to you. Okay? So let's set up our ice table first. And again, we're only focusing on the first deprotonation step. So notice here that I'm only showing the first deprotonation step. Now let's plug in our initial concentrations. We're given the initial carbonic acid, and our hydronium and bicarbonate are approximately 0. Next, which direction is the reaction going to proceed? Well, we've got zeros over here, so the reaction must proceed from left to right. And that tells us that the changes on the reactant side are going to be minus X, decrease, and on the product side, they're going to increase, plus X. So our equilibrium concentrations would be 0.03 minus X on the reactant side, and X on our product side. So now let's write an equilibrium expression. We already did that, a Ka1 expression for the first dissociation step. Now let's plug in our equilibrium concentrations. We use Ka1 given in the problem, and we plug in X and 0.03 minus X into our Ka expression. Now let's take that Ka expression and solve for X. Now I'm going to make an assumption here to simplify the math. I'm going to assume that this minus X is negligible when compared to the initial concentration of carbonic acid. So when I do that, I can just simply negate this or neglect it, and my equation simplifies, as you can see here. Now we can't negate or neglect these that are multiplied, just the ones that are added or subtracted. So now we can solve this much easier, and we end up with an X value of 1.1619 times 10 to the minus 4. Now, I'm not rounding to the correct number of sig figs here. We would only have 2 because this isn't my final answer. Okay, but I've underlined the 1 here to indicate that that is the only 2 sig figs. So that's my X value, but we need to check. We made an assumption up here. Is that assumption valid? Well, we need to check to see if X is indeed negligible. I take my value of X, and this would be the change, X, divided by the initial concentration of carbonic acid times 100, and I get 0.39%. If that percentage, when we compare our X value to the initial concentration, if it's less than 5%, then that assumption is valid. Now we could go back and we could solve this using the quadratic equation, and if you're more comfortable solving these without making the assumption that we did before, we could solve it using the quadratic equation just as we've done plenty of times. We should get the same answer. Okay. So now we have our X value, and let's plug it into our ICE table. So let's plug X in here to get our concentration of carbonic acid, subtract it from our initial, and we get 0.03 molar. Now we'll plug X in here for X, and X for hydronium and bicarbonate, and we get the hydronium produced from the first dissociation step is equal to X, and the bicarbonate is also equal to X. Now, as we mentioned before, these that we've calculated here are not our final concentrations. We may produce some more hydronium, and we may lose a little of this bicarbonate in our second dissociation step. So we've done these calculations, but please make a note, these are not our final concentrations of hydronium and bicarbonate. So now let's move on and set up our second ICE table and look at the second dissociation step. Okay? So our second ICE table will focus on the dissociation of the bicarbonate ion. So let's plug in our initial concentrations, and this is a little different. My bicarbonate, the initial concentration for the second dissociation is equal to X, 1.1619 times 10 to the minus 4. And notice that hydronium is not equal to 0 because we have some already present while this second dissociation step is occurring. So please pause the video if you're not clear on that and think about that a little bit. We're not starting with hydronium at 0 when the second dissociation step is occurring. And our bicarbonate ion is, of course, equal to X, what we produced in the first step. So now which direction will the reaction go? Well, carbonate ion is 0, so we must go in that direction from left to right. So we're going to have minus X on the reactant side, plus X and plus X on our product side. And now we can get our equilibrium concentrations. You can see those here. Next step, is to set up a Ka2 expression based on our second dissociation step. Then we're going to plug our equilibrium concentrations into that. Notice that we're using Ka2 and we have our equilibrium concentrations for our second dissociation step. Now, let's solve this. Let's make our assumption again that this x here, the minus x, is negligible when compared to the concentration of bicarbonate, which we have here initially. Okay, so let's assume that's negligible, and that simplifies our expression, as you can see that here. Well, we can solve this pretty easy. We've got the same number, so those just cancel, and x here is equal to 4.7 times 10 to the minus 11th. Let's check to see if that assumption is negligible. Let's take our x value and divide it by the initial concentration of the bicarbonate ion times 100, and we can see that our percentage here is indeed very much less than 5%, so we can assume that is negligible. Now again, if you don't like making the assumption that x is negligible, you can solve it as you have before using the quadratic equation. Okay, this is just a shortcut that you can sometimes take, but not always. Now that we have our x value, let's plug it into our ICE table and see what we've got. So let's plug it in here and subtract x from our initial bicarbonate ion concentration, and we get rounded to 2 sig figs, 1.2 times 10 to the minus 4. So now this is my final bicarbonate ion. Again, we don't have two bicarbonate ion concentrations, just one, and that's our initial minus anything we lost in our second step. Now hydronium, we need to figure out the hydronium ion concentration, so we just take our initial here from the second dissociation step plus x, and we get 1.2 times 10 to the minus 4. Now again, this is what I'm circling here. This is my final hydronium ion concentration. We only have one hydronium ion concentration for any polyprotic acid. Just like any regular acid, monoprotic acid, you'll only have one hydronium ion concentration, not two. And the carbonate ion concentration will be equal to simply x. So we have those. Now we were asked a couple of other things. We were asked to calculate the pH. So we'll base the pH only on the final concentration of hydronium. We take the negative log of hydronium. Again, we can only have one pH in this solution. I stress that because that's a common mistake. So our final pH, our only pH in this solution, is 3.92. And we were also asked to calculate the concentration of hydroxide. So we take Kw divided by hydronium, which again, we use the final concentration of hydronium to get our hydroxide. So here we have all of our concentrations of all the different species. All of these species appear when we have this diprotic acid dissociating according to two steps. So here's all the final concentrations, equilibrium concentrations. Be sure you can recognize polyprotic acids, understand their dissociation, and be able to calculate all of the equilibrium concentrations of all the species that might be present in a solution.